Hello everyone, welcome to CivilPrep. I am Krishna Gupta, and this is a session on MentorQuest at the rate 500, where we'll be looking at 500 live answer discussion and their writing. Okay, so friends, I would like to update you that we are starting this session. Okay, you can join this session uh, by by clicking on the link which is provided in the description. Okay, you can also enroll in the course. Okay, you can join a YouTube channel which is provided here. The QR code is present here for the YouTube channel, and you can also look at the Telegram group where we are actively discussing answer writing sessions. Okay, so first question which we have here, that is, critically analyze the contribution of paleomagnetic data in understanding the evolution of continents and oceans. Now, here in this diagram, we can see that there is an movement of the continents as well as oceans. Okay, so this is something which has happened in the past, and which is currently also happening, and which will happen in the future also. So this is, we can say, this is the current aspect, and this is an area which is almost around 250 million years ago, when there was Pangea, which was a supercontinent, and currently we have different continents which are spread apart from each other in the contemporary time. Okay, so looking at this question, we also have a question from PYQ, that is, evidences for paleomagnetism and seafloor spreading have validated the continents and ocean basins have never been stationary. Elucidate with suitable example and diagram. So this was the question which was asked in 2023. Guys, you can stop the video and you can write the answer. After writing answer, do provide your answer in PDF form, or do write provide it in the comment box, and we'll discuss it. Okay, friends, so let's start writing the answer for this question. Now, here we are looking at something which is from the paleomagnetic data. Okay, so we will start it from a research perspective, that is, research by Crosswick. Okay, he has employed paleomagnetic reconstruction to refine supercontinent models like Rodinia and Pangea. Okay, so here we'll be seeing that the paleomagnetic data, it is derived from remnant magnetism, which is preserved in rocks, certain continental drift aspect, or we can say evidences, ocean floor expansion, and also polar wandering. So here we see that it is giving us credence both to the Alfred Wegener's early insight and later plate tectonics model, which is provided by Wine, Matthews, and Wilson. Okay. Credence to continental drift provided by Wegener and plate tectonic theory by Tuzo Wilson, Morgan, etc. Okay, guys, so this was the first part of the question, which was introduction, but it includes recent data with respect to the researches which is currently going on. Now, let's look at this model here, which is providing us an evidence of the recent concept. Okay, I think something is not working here. So we can say the same thing here in this model here. We can see how the continents are drifting apart, and this is resulting into the formation of Pangea first. Then the Pangea is getting disintegrated, and this is resulting into the formation of current, we can say current settings of continents and oceans, which is present here. Now, looking at the further part of answer, that what is paleomagnetic data and global evidences. Now, here we'll be saying that the paleomagnetic data, it involves the studying the orientation of Earth's magnetic field recorded in rocks. Recorded in rocks. So which rocks? At the time of their formation. It is basically a part of paleoclimatology, which reconstructs the Earth's climate and tectonic past. Okay. Now, looking at the global evidences, here we'll be seeing that we have one of the mountains, that is the Appalachians and the Chalcedonian mountain alignment. Caledonian mountains and their alignments. So here, Bullard is one of the theorists. He has used the paleomagnetic profiles to align the continental shelves, supporting Pangaea's assembly. So here we'll be seeing that here we have North America. Okay, and here we have Europe. And here we have Africa. So here we'll be seeing that we have Appalachians at this region. And here we have mountain ranges, which are of Caledonian Mountains. So this was the first evidence where we see that the continental shelf of the region, it was aligned here. So this was the first, we can say, evidence which was found globally in terms of the paleoclimatic data. Now, number two, here we have glacial strations in Gondwana. So this study, it was done by Du Toit. So Du Toit, he identified South Polar glacial evidence. Okay, South Polar glacial evidence across the countries like, or continents like India, South Africa, South America, and he explained that unified landmass by the continental drift. So here we'll be seeing that this is the Gondwana land. Okay, here we have different countries here. Okay, so what he has provided that the region which was almost around 60 degrees below the south of the latitude. So here there was the presence of glaciers. So this was one of the evidence which was provided by Du Toit. Okay. Now, in the next part, we'll be seeing the third evidence, that is the basalt magmatism on mid-Atlantic ridges. Okay, we are trying to write a very specific answer here. So here theorists like Wine and Matthews in the year of 1963, they discovered symmetrical magnetic stripping on the ocean floor, which was crucial for the seafloor spreading. Now, when we move further, we need to provide the contribution to continental and oceanic evolution. Contribution of paleomagnetic data for continental and oceanic evolution. Now, number one will be saying that is seafloor spreading model. This was initially provided by Harry Hess, and later the model was developed by Vine and Matthews. Okay, so they provided that the magnetized oceanic crust records polarity reversals, validating divergent plate boundaries and ocean basin expansion. So here, the ocean basin expansion, it is recorded here, then validating the divergent plate boundary where near the boundaries, here we'll be seeing that there is presence of mid-oceanic ridges, and in the rocks or ridges, there is presence of polarity reversal. That is, if this is north, south, north, south. So this was something which was validated here. So here we can see this is found in the magnetized oceanic crust. Now, second evidence we'll be seeing here. That is polar wandering paths. So here we'll be seeing that the polar regions, for example, this is North America, this is the region of Siberia. So here in the past, there has been shifting in the poles. Okay, so for example, this is a different part here, and this is another part. So two parts were identified, but when they were matched, it was seen that both the paths they were identical. So here what we see, what it was, the conclusion was seen that it is not the poles which is wandering, but it is the continents and oceans which are moving. So this was provided by the polar wandering paths. Okay. Now, number three, third point. Here we have supercontinent cycle. This was first provided by plate tectonic theory. Here, Morgan, Wilson, Mackenzie. So they were the first proponent for this supercontinent cycle. So it was seen here that the paleomagnetic orientation data, it helped the breakup and amalgamation of supercontinents like Rodinia almost 550 million years ago and Pangaea almost around 250 million years ago. Okay, so these were certain models which helped in predicting that what was the orientation of particular continents and oceans. Now, here we'll be concluding this answer. So here we'll be saying that the paleomagnetism has emerged as a one of the important tool in understanding the tectonic geoscience. Which is providing empirical data for understanding the processes like continental drift, seafloor spreading, mountain building, and supercontinents. Thus, we'll be seeing that this data, it is quite reliable as evidenced for predicting future changes or evolution of continents and oceans. So this is one of the answer which we can see here, which suffices the question here. That is critically analyze the contribution of paleomagnetic data in understanding the evolution of continents and oceans. Okay, guys. So this is first question. Now, moving to the next question here, we have critically evaluate the geosynclinal theory as a precursor to modern plate tectonic theory. Now, a question which was asked in the previous time, evaluate how far Kober's geosynclinal theory explains the mountain building process. This was asked in 2018. So guys, do write the answer. Take your time, take 7 minutes and send the answer to me. Okay. You can pause the video here and you can start writing the answer. Now, friends, let's write an answer to this question. Now, this is one of the question which is asking us to critically evaluate the geosynclinal theory as a precursor to modern plate tectonic theory. So we need to provide that how this geosynclinal theory it formed, it basically developed, and it became one of the important theory for the explanation of various geophysical phenomena. So here we can introduce the answer by the geosynclinal theory developed in 19th century with James Hall and Dana, who emphasized sediment accumulation and lateral compression. So here we'll be seeing that this is a geosyncline. Here we'll be seeing that there is sediment accumulation is taking place. And this is resulting into the subsidence and later on by the lateral compression, okay, resulting into the rise of this geosyncline into the fold mountains. So this is a geosyncline. Okay, this is also geosyncline, but it is now fold mountain. This is provided by Holland Dam. Okay, now after this, what we see here that there was later on there was Kober's model, who provided his theory in 1921. So he introduced the foreland and geosyncline dichotomy. Where the rigid forelands compress mobile belts. Okay, we'll understand this theory in detail. Now, later on, there was Holmes, that is Arthur Holmes, in 1944. That is, we can say under the development of quantitative revolution, he added thermal convection as a driving force. Okay, and he shifted the paradigm towards endogenetic mechanisms. Okay, so this was the early model of the theory which was developed here. But what we will see here that there was something in the model which was quite missing. So despite the mechanisms such as number one, horizontal crustal movement, these models, they stressed more on the compressional forces, number two, crustal instability, number three, sequential uplift. All these things, it was later refined by plate tectonics or plate tectonics model. Okay, now looking at the formation of the geosynclinal theory, or looking at the question again, evaluation of geosynclinal theory as a precursor to the modern plate tectonic theory. Now here we need to elaborate on the geosynclinal theory which developed before the plate tectonic theory here. Okay, friends, so moving to the next aspect, we need to look at geosynclinal theory and plate tectonics linkages. So here we'll be seeing that the first aspect which is explained here by the geosynclinal theory, that is the orogenesis. So under the orogenesis, the geosynclinal theory, it highlighted the linear belts of sedimentation, and along with it, the deformation, which is closely mirroring the modern concept of convergent plate boundaries. So here we'll be seeing that there is a presence of a Benioff zone. So this Benioff zone, it represents inclined seismic zones near trenches. Okay, thus it bridges the gap between static model and dynamic subduction mechanism. Now, apart from this, we'll be looking at the second part, that is sedimentary basin as tectonic markers. Now, in this aspect, we'll be looking at whenever there is a subducting plate and there is a convergence which is taking place either in the oceanic convergence or oceanic continental convergence. Here we have one aspect, that is the presence of or the formation of a accretionary wedge which is also called as back arc basin. Now, the formation of this back arc basin or the accretionary wedge, it is explained both by the geosynclinal theory plus the plate tectonics theory. Okay, so here we'll be saying that this back arc or fore arc or fore arc or intermountain basin, it is governed by subduction and slap pull mechanism. Okay, so here we see that an example for this part, that is Andean type continental margin, which is explained by both the geosynclinal theory and the plate tectonic theory. Basically, what happened in the Andean part here, we can understand this with a diagram. So this is a South American plate and this is a Pacific plate. This is asthenosphere. Because here we'll be seeing that there is presence of water. Okay, there is certain amount of water will be present here. Second thing we'll be seeing that there will be presence of accretionary wedge, and because of the presence of water, the magma, it will become molten and it will result into the formation of the volcanic mountain ranges. But here there is a catch. That is, number one, initially, that is almost around 70 million years ago, the movement of this, it was very fast. Oh, sorry, it was very slow. So there was formation of the first volcanic mountain range. But we see here that almost around 30 million years ago, this became quite fast. Okay, so this resulted into the formation of a intermountain plateau. Now, when this plate subducted more, almost around 20 million years ago, this again became, the plate big subduction became quite slow. So this resulted into the formation of the Andean type of mountain ranges here. So we see here that there is two mountain ranges, and between this there is presence of intermountain basin or intermountain plateau. So this is the type of plate which is formed between the Andes mountain ranges. Now, third part when we'll see here, there is paleomagnetism and seafloor spreading. So under the paleomagnetism and seafloor spreading, we have certain theorists, for example, Wynne and Matthews, Harry Hess. Then under the plate tectonic model, we have Mackenzie and Parker. Okay, so they are related to the development of this paleomagnetism and seafloor spreading theory. So here they specifies the magnetic anomalies. And rigid lithospheric plate, which is moving over asthenosphere. Okay, so because of this, what we see that there is a replacing, effectively replacing of subsidence, which is based on interpretations with dynamic models like plate tectonics, which is seen in the empirical evidence of contemporary times. For example, Atlantic Basin. Here we have here we have the presence of mid-oceanic ridges, which is present almost parallel to the MOR. So here we'll be seeing that whatever the magnetic anomalies are, it is parallel to mid-oceanic ranges of Atlantic Ocean. Okay, so here we see that this is also one of the part which is providing us that yes, the seafloor spreading is taking place here, and there is presence of paleomagnetism over the rocks. Okay, now when we look at this aspect from the critical perspective, here we'll be seeing that for the strength of geosynclinal theory. Number one, it is a precursor to identifying tectonically active belts. Number two, it emphasized spatial localization of orogenic activity. For example, Himalayas, Alps, and Atlas. Number three, it served as a foundational geological paradigm. In the pre-seismology and pre-paleomagnetism era. Now, when we look at the limitations, here we'll be saying that it lacked the driving mechanism. For example, convection current, number two, it did not account for oceanic crust dynamics. That is, we will see here the various features of ocean basin. Number three, there was an over-reliance on vertical movement. That is aperogeny and subsidence. While neglecting lateral compression. So this was another aspect which was seen as the missing part in the in this theory here, that is the geosynclinal theory. Now, let's move to the conclusion. Concluding here, we will see that geosynclinal theory is considered as obsolete now. Which was basically developed in the classical era. Now, but we will see here that it contributed particularly for sediment accumulation, mountain building process, and the development of intermountain basin. Or plateau. Thus, it paved the way for the development of plate tectonics theory, which basically developed in the quantitative revolution period or quantitative revolution paradigm, and helped in the explanation of Earth's dynamic crust. So guys, here we can see that this part, it explains us that how there was the development of the geosynclinal theory. Okay, and here we'll be also seeing that how it became one of the precursor for the development of plate tectonics theory. So this is the answer for this question. So guys, we'll be looking at other answers in the next phase. Okay. So do share how did you like the video, and we'll look at it further. Thank you.